the postdoc seminars. So of course, our first one is not a postdoc. We have Cynthia Rudin here from Duke. So I had printed out an introduction of her from a few months ago, and she's won like 15 new awards and gotten promoted and named a lecturer since then. So it's wildly outdated already, but I think that just speaks to the quality of work that Cynthia does, and we're really excited to have you here today. So thanks so much.
Thank you. Okay, hi everybody. So I'm going to talk about interpretability. My lab works on interpretability. So in particular, I'm going to talk about decision trees and scoring systems, which are sparse linear models of integer coefficients. Okay, so for the purpose of this talk, an interpretable model is a function that fits on a PowerPoint slide and can be computed without a calculator. Okay, so why do we care about having a function that fits on a PowerPoint slide and where you don't need a calculator to compute it? Well, there's a lot of different reasons, and I've listed a few of them, which are first, it's really hard to trust a model that you don't understand what it's doing. It's also really hard to troubleshoot a model when you don't understand what it's doing. It's much easier to troubleshoot a model when you know what it is doing. Also, it's very helpful to have models that are easy to compute. Like, can you imagine a judge sitting in a courtroom trying to get their calculator out and calculate some risk for some person who's standing in front of them? Like, that's a huge waste of time, right? You'd want the judge to be able to look at this, have the function memorized and just compute it off the top of their head. Or like a doctor working with a patient, like you don't want the doctor to have to get a calculator out. Also, what we've found is that as long as the data come with a naturally good representation, there doesn't seem to be any loss in accuracy for these very interpretable models over much more complicated models like decision trees or neural networks or anything like that. It depends on the data representation. Like it wouldn't work for say, computer vision, but it would work for, say, data where the features are meaningful and the representation is kind of as good as it's going to get. Okay, another reason you want to care about interpretable models is to avoid what I call the North Point fiasco. So back in 2015, there was this article written by the ProPublica group, which is now very famous, where they accused a model of being racially biased. And that model is called COMPAS. And COMPAS is used very widely across the US justice system. And they gave some examples of where COMPAS gives predictions that don't make any sense. And so ProPublica accused this model of being racially biased. And the model is proprietary. And so what ended up happening was that nobody could actually figure out whether it was racially biased or not. And after this huge amount of discussion, people basically said, COMPAS may still be biased, but we can't tell. So it might be, it might not be. We don't know what variables are actually involved in this model. Now, North Point's product that they're selling to the justice system is a black box machine learning model. So I can ask, well, does North Point have better machine learning tools than the rest of us? I guarantee the answer is no. And then also, were they held responsible for proving that no transparent model exists that's as good as their proprietary model? And of course, no. And in fact, it's not in their best interest to try to prove this because it would destroy their business model. Now, recidivism prediction, so predicting whether someone's going to be arrested in the future, that problem is actually one of these problems where it doesn't matter which machine learning method you use, they all kind of tend to perform the same. So the main factors are age and criminal history. So I put up a model here. It's a predictive model for 2-year recidivism. The model is, as you can see, it's very simple. It's just how old you are and how many prior crimes you've committed. So it's like if you're 19 to 20-year-old and you're male, then predict arrest. Also, if you're 21 to 23 and you have 2 to 3 prior offenses, predict arrest. This is arrest within 2 years of your COMPAS score calculation. Also, if you have at least 3 prior offenses, predict arrest. Otherwise, predict no arrest. So it's a very, very simple model. And that particular model, we built that model from the ProPublica data in less than 10 seconds. We certified this model to provable optimality over the space of models of this form in less than 2 minutes. And this model happens to be just as accurate as the model that's used in the justice system, this compass model that North Point has been selling to the justice system. So as it is used in Broward County, Compass, this proprietary model that may depend on race and may not, is exactly as accurate as that. And the machine learning algorithm that created this model and proved it to certifiable optimality is called certifiably optimal ruleless, and it's an algorithm that I will be telling you about in this talk. Okay, so again, that's the whole machine learning model, and it selected those variables from a much larger collection of variables, and it selected what order to put those rules in. All right, so it makes you wonder why we need these proprietary models in the justice system, because they're not giving us any more accuracy than these very, very simple models. Now, I've been working on predicting arrest or predicting recidivism since well before that ProPublica article came out. And this is a result on a data set that we've been using since about 2014 from the National Institute of Justice, that where the goal is to predict 3-year recidivism. So it's when a person is released from prison, we want to predict whether they'll be arrested within the next 3 years. And this is a different form of model than on the previous slide. The previous slide showed you a kind of decision tree, a very one-sided decision tree, whereas this is a sparse linear model with integer coefficients. So these five conditions in this model, you would check them, and then the person gets assigned points based on whether those conditions hold, and then the number of points translates into their risk of being arrested within the next 3 years. And the machine learning model that created this scoring system had to select these variables from a much larger collection of variables, and it also had to select the number of points that goes over here. And so this is a model that you don't need a calculator for. You can just add up the points here, and then use the number of points to get the risk from this table down here. All right, so this particular model was created in 20 minutes with a 2.7% duality gap, and I'll tell you what that means later. But it's if we ran it longer, that duality gap would go to 0. And the method that created this model is called RiskSlim, or risk assessment super sparse linear integer models. And I'll tell you about this algorithm also during the talk. And here are my collaborators. Okay, so let me start by discussing the Corrals algorithm, which is an algorithm for optimal one-sided decision trees, or decision lists, or rule lists, or whatever they're called. So here's my notation. I'll start with, this is vanilla binary classification with binary data. We have been working on generalizing it to real value data, but for now, we're working with binary data. So these are the covariates, or variables, or features, whatever you want to call them. They're all binary. And x and j is the jth feature of observation n. And then y are the labels, which are were you arrested or were you not arrested within 3 years of your release. A rule list is denoted by a collection of rules. And each rule is an antecedent followed by a consequent. So in the rule list, this is the notation for the rule list. So this is a collection of rules, R1, R2, R3, R4. And each rule is an antecedent and a consequent. Okay? So that's the notation for a rule list. And then DP is a prefix, which is a collection of antecedents. So DP is just this part of the rule list, the antecedents. And then delta P are the consequences over here. And Q0 is not included in any of this. That's the prediction for the default rule. So if you don't fit into any of the rules, you get your prediction made by the default. Okay, so this is the objective that Corrals is trying to minimize, which is a combination of the fraction of points that are misclassified and the sparsity of the model. This is actually the fraction of points that are misclassified. It's not an upper bound for it. So it's like a 0-1 classification error. And this is actually the number of rules in the list. So this is like an L0 regularization term. This lambda is a regularization parameter. And we usually just set it to 1% because we would be willing to trade 1% error for one fewer rule in the list. And you can cross-validate the parameter if you want to, but we found that you can just set it and that works perfectly fine. Because that's approximately where we want that trade-off to be anyway. Now, in the notation that I'll show you later, we write this as being the loss plus lambda times the size of the rule list, the number of rules, which is k. Now, our goal is to minimize this objective over all rule lists, which means that we have to consider every possible size of rule list and every possible subset of rules of that size and every permutation of every subset of rules of that size. And so it's a very hard combinatorial problem, and there's no polynomial time approximation for it here. Okay, so we're going to actually try to solve this problem anyway, because we figured out that we can actually do it. All right, so here's some more notation. This captured function is it's a binary. It's got binary outcomes. It's a condition. So this is captured as 1 if the antecedent pk is true for xn. So this might be it's captured if the age is between 21 and 23 for that particular individual. And then this is captured in the context of rule list dp. Okay, so what this means is that you didn't get captured in any of the previous rules, but you did get captured in rule k. So for instance, if k is 4, then you would be captured by rule 4 in the context of this list if you were not captured by this condition, that condition, or this condition, but that you were captured by this condition. Okay, so you're captured in the context of that rule list. And then, again, here's my objective. And the loss term can be broken into two pieces. You can have a loss for the rules in the list and a loss for the default rule. So let me write those two terms out so you'll see what they are. This loss says that we're going to try and find all points that for all rules are captured by some rule, but that are misclassified because their label doesn't equal the label of the rule that they were captured by. So they are misclassified. And the other term says that these are the classification errors we make on points that were not captured by any of the rules in the list and whose label does not agree with the default rule's label. So they're misclassified by the default rule. Okay, so these are, the first term is misclassifications that occur here, and then the last, this other term is misclassifications that occur here. Okay, now we made several observations about this very, very hard problem that led us to reduce the size of the search space by a large amount. So our algorithm is a branch and bound algorithm, and it proceeds to sort of block off big chunks of the search space to reduce its size. And then for the remaining part of the search space that we search it very, very quickly. So I'm going to show you several theorems that are the bounds that reduce the size of the search space. The first bound is called the support bound, and it says that each rule in an optimal rule list has sufficiently high support. So let us consider an optimal rule list, D star, which minimizes our objective. D star is represented by the antecedents, the consequence, the default rule, the label of the default rule, and the size of the rule list. Now for each rule in the list, the support of that rule has to be at least 1% of the data, 0.01. Okay. So each rule has to capture at least 1% of the data, and that, otherwise it's not an optimal, can't be an optimal rule list. And the support, again, is the fraction of points that are captured by that rule. Okay, so if a rule doesn't capture enough points, it can't be optimal. Can't be part of an optimal rule list. So it means we only need to consider antecedents that support at least lambda, support at least 1%. Okay, so knowing that information, we said, also, there's a theorem that we designed that says that the VC dimension of rule-less classifiers actually equals the number of antecedents we're considering. So if we increase the lambda value, that means we have fewer rules that we're considering because they have to have support at least lambda. And because of that, we've actually reduced the VC dimension of the set of functions we're working with. So we've actually simplified the problem directly by increasing that regularization parameter. Okay, so anyway, as we looked at this information, this to us means that we only need to, we can create a giant pile of possible antecedents and just choose from there to create the rule lists. And so that's what we did. And we leveraged kind of algorithms that have been available from the data mining community for like 30, 40 years, right? The data mining community has built these beautiful algorithms for frequent pattern mining. And those patterns, are, you tell it how frequent you want the pattern to be, and it will produce all patterns of that frequency or above. And those algorithms are called a priori, and the latest one is FP growth. And so we can grab one of these algorithms, and they run very quickly, and they just mine the whole database for possible rules that we can put into our rule lists. So that's the first step of the algorithm, is just mine all antecedents with support at least lambda. So we start with a giant pile of rules. And these algorithms all run very quickly, and they all produce the same result. They just find all patterns that are sufficiently frequent. And so it doesn't really matter which algorithm we use for that. Okay, so once we have our giant pile of rules, we have to assemble rule lists from them. And we're going to do it from the top down. Now, to reduce the size of the search space, we're going to prove that certain rule lists and all of their children, all of their extensions, are suboptimal with respect to our objective. Okay, so the first bound to do that is the accuracy bound, which says that each rule in an optimal rule list must correctly classify at least 1% of the points. Okay, so I want you, again, to consider an optimal rule list, which minimizes their objectives, again represented the same way. Then for each rule in the list, it has to be captured and correctly classified at least 1% of the time. And if not, it is not part of an optimal rule list. And so it means that if we are constructing this rule list, as we construct it from the top down, if we come across a rule that's not sufficiently accurate, we don't bother extending it, because it's never going to create an optimal rule list. Okay, the length bound says that optimal rule lists are not too long. That shouldn't be surprising because we have a regularization parameter and it does something. And so it prevents the rule list from getting too long. And we have an explicit length bound on this. And the length bound is actually tightened if you include your progress so far, and a bound on the objective. So here's the tighter version of the bound I just showed you. So RC is the current best objective. M is the number of antecedents we mined from the data set with the pile of rules. And then our objective is R. And then this thing is a lower bound on R, which is composed of the regularization term. And then instead of the full loss, I'm just including the loss on the rules, and I'm not including the loss on the default rule. And so that's why it's a lower bound. Because if you add in that extra term, L0, then you get the full loss function. And so if you take this lower bound into account, it actually tightens our bound on the length of the optimal rule list. The one-step look-ahead bound has been very, very helpful in practice in reducing our computation time. And it says that if a prefix is lower bound is within lambda of the best current objective, then adding any rules to it will lead to a non-optimal rule list. So in other words, you're growing your list, and you realize that if you add one more rule to it, then no matter how good that rule is, it's just not going to be better than the best thing you've seen so far. So you might as well not even go there. The rule list is just not accurate enough for how long it is. Okay, so again, let dp be the length key prefix. The lower bound is the same one that I just showed you without the term for the error on the default rule. RC is the best current objective value. If the lower bound plus lambda, which you get an extra factor of lambda from adding one more rule to the list, if that is bigger than the current best objective you've seen so far, sorry, if this is higher than the current best objective you've seen so far, it's worse than that, then any rule list you can construct that extends dp is provably suboptimal. In other words, it's going to be worse than the best thing you've seen so far, so you should not even bother trying because you're not going to get any better. Okay, so in other words, if any prefix is not accurate enough with respect to its length, don't bother extending it. The equivalence points bound has been also incredibly helpful, but the notation is a little bit difficult, so I'm just going to explain the intuition to you. Let's say that you have two identical observations in your data set, and one of them is labeled positive and the other one is labeled negative. Then there's no possible way to get them both classified correctly. There's just no way, because if you classify that point as positive, you miss one. If you classify it as negative, you miss one. Now, if you have 10 points that are all classified the same way, if you have 10 points that are all identical, and they are not all classified the same way, you're going to get some of them wrong. And in particular, you'll get at least the minority class of them wrong. You could get the majority class wrong, but you will get at least the minority wrong. And that's what the equivalent points bound says. It just says that if you have equivalent points, then you'll get at least the minority label wrong. And this bound has actually been very, very helpful, particularly in the recidivism data sets where you often have people of the same age and that have very similar criminal histories, like number of priors. So the permutation bound,
So one question, is there any notion of uncertainty here? Because from what you said, it would mean that you essentially cannot make a prediction for these guys. So instead of getting them right or wrong, you could say that, I have this, I'm quite uncertain about. I don't want to make a conclusion. Could you say that?
No, you wouldn't do that. So in machine learning, you often assume that the data are noisy, that the labels are noisy. There's always some, if for each x, all the points were always classified the same way, that's a non-noisy case that we assume never happens in reality. So we would simply try to make the prediction anyway and try to reduce the classification error as much as we could. And then using statistical learning theory, we would get bounds on the quality of our predictions on the test set. But you don't simply give up on any point that has,
But I mean, isn't that problematic from a purely from a law perspective? So I don't want to misclassify, because like you said, I will get at least a minority wrong. So I don't want to do that. I don't want to send someone who is innocent to prison. So
no, it's just minority of the points that have the same covariance in different labels. It's not about other types of minorities. Maybe I didn't understand your question, but
so, I mean,
just because there's uncertainty doesn't mean you can't make a prediction.
But it would mean that wouldn't you want to also make a statement about how certain you are about your prediction, not just a point prediction, but maybe a confidence interval or something?
Oh yeah, you can definitely make confidence intervals on your predictions, but that's, how do I say this? The goal of this particular algorithm is just simply to make predictions, and the uncertainty quantification is on the overall accuracy, not on each individual prediction. If you wanted to get a quantification for each individual prediction, there's two ways to do it. The first way is to look at the number of points in each leaf and calculate the probability from the points in the leaf. So that would, in other words, you could calibrate the tree to the data. And then the other thing you can do is go to a fully Bayesian approach, which I will show you in a few minutes. Okay. All right, so the permutation bound is led us to have to do quite a lot of extra work, but it also was very helpful in practice. Now, it turns out that if you have two rule lists that are made of the same rules, and one is more accurate than the other one, one's a permutation of the other, and one's more accurate, then it turns out you only need to look at the more accurate one and work on extending that, because the less accurate one will never, ever produce an optimal rule list. So for us, what that meant was that we had to keep track of every subset of rules we'd ever seen and the best permutation of that subset of rules that we had ever seen. So we had to create a special data structure to do this, which we call the symmetry-aware map. Okay, so the theorem says, which I didn't put the notation for the theorem, but it says that only an optimal permutation of a prefix can lead to an optimal rule list. And so in practice, what that means is that when we see a new set of rules, a new prefix, then we have to go look it up in this data structure we created, symmetry-aware map. And then we have to, that symmetry-aware map will tell us if we've ever seen that set of rules in a different permutation before. And if we haven't, if there's no permutation of that set of rules in the data structure, we add it to the symmetry-aware map. Else, if the new permutation is actually a better permutation in the symmetry-aware map than the one that's already there, we replace it. And if it's worse, if it's a worse permutation, we're done. We're not going to extend it. We've already handled that. Okay. So here's the full algorithm. We have three data structures. Our trie, which keeps track of all of the computations we've done to construct intermediate trees. Our symmetry-aware map, which keeps track of the permutations of all prefixes. It keeps track of the best permutation of every prefix we've seen. And a queue, which tells us in what order we need to traverse the set of trees. Sorry, the queue tells us in what order we need to start extending the children of all of the prefixes we've seen so far. And then we use our data mining algorithm to mine all the possible rules, compile the rules, and then we put all single rules into the queue as possible trees. So we start with rules of size 1. While the queue is not empty, take the current prefix from the queue, consider each of its children, add one more rule to it, and check the lower bound against the current best. We check the length bound, is it too long? We check, is that new rule we added, is that accurate enough? If it's not, we throw the prefix out. The one-step look-ahead bound, is the rule list accurate enough for how long it is? The equivalence points bound is helpful in keeping our lower bound nice and tight. And then the symmetry-aware pruning, which helps us make sure that we're looking at the optimal permutation for that set of rules. Now, if the lower bound is higher than the current best, the prefix is no good. We've proven that the prefix is no good. Otherwise, we take this new rule list and add it into the queue because that rule list could potentially be extended to be the best one. And then if the current objective is lower than the current best, that means we found the best thing that we've seen so far, and so we just update the current best. Okay, and then at the end of all of this, so we continue to add things to the queue, and then process them one by one. When the queue is empty, it means we've either searched the entire space or eliminated it, and we are done. And the output is an optimal rule list with a certificate of optimality saying that we found the best. possible meanings. Okay, and as I mentioned, for a lot of different problems, it doesn't seem to matter which machine learning algorithm you use, they all tend to perform the same. And recidivism prediction is one of these problems. So this is the ProPublica data I was talking about earlier. And this is a whole bunch of different machine learning algorithms on this data set. I should have put Compass on here, but Compass is sort of right around the same. And then the different dots are for different folds of the data set. So that's why they're all, the colors don't mean anything, it's just what fold we were working with. This is tenfold cross-validation. And as you can see, some of these methods like boosted decision trees or support vector machines with radial basis function kernels, these methods produce very, very complicated classifiers that are difficult to understand, whereas the Corals model is the one I showed you on the first slide of my talk, which is just, a simple combination of age and number of prior crimes. And I'm not advocating that we should switch over to the simple model, I'm just saying we don't need proprietary models. The weapons prediction problem is another problem where it doesn't seem to matter which algorithm you use, they all kind of perform the same. Maybe CARD and C4.5 are not quite as good, but those are older algorithms. And again, some of these models are very complicated, you can't figure out what they are, whereas the model for Corals is pretty simple. There's one of them. So basically you're trying to predict whether or not a weapon is going to be found in someone who is not frisk. And the model just says, are they at the transit authority or do they have a suspicious object or a suspicious bulge? And that's it. That's the whole model. All right. So when you see these pictures, it kind of makes you wonder, again, why are we using proprietary models like Compass? It's not clear that we actually need them. Okay, so this is an ablation study where we took the Corals model and handicapped it in a whole bunch of different ways to see which pieces of it were helping us the most. Okay, so along this axis is time, and this axis shows the count of rule lists that are in the queue of particular sizes. So at the beginning, we put all the rule lists of size 1 into the queue. And then as we process them, some of their children end up back in the queue as a rule list of size 2. And so as those get added into the queue, we're over here, and then the queue gets bigger because it's having more and more rule lists in it. And then size 3 and size 4 over here. And then after 149 seconds in this run, Corals proved that it had found the optimal solution, and it stopped. And so that's this point in time right here. Okay, so then what we did was we took away Corals' symmetry-aware map. And in that case, it still finished with, looking at rule lists of up to size 4. But we lost a factor of 9 in the total overall time. And then we put that back, so put the symmetry map back, take out the look-ahead bound. And in this case, we started looking at rule lists of size 5, even though the look-ahead bound would have allowed us to prove that those rule lists were suboptimal. And we lost a factor of 12 in the overall time. And then if we took out the equivalence points bound, it's just a mess, and you start looking at rule lists up to size 9, even though this bound could have proved to you that you would never need those. And it took a really long time, and we didn't run it long enough to show you the full extent. Okay, so, and I should mention that the different pieces of Corals are actually more or less important for different applications. So some applications, equivalent points is not as helpful, and the look-ahead bound is more helpful. Okay, so what Corals' strengths are that it actually proves optimality, which is more than you can say for CARD and C4.5 and the other decision tree methods. And it runs very quickly because of all the work we did in creating these theorems and the data structures that work together to try to reduce the overall time. But it can't really do probabilistic predictions unless you calibrate the data to the predictions, which nothing wrong with that, but not exactly what it was designed to do. It also doesn't place higher risk subgroups first. When you're looking at decision trees, it could be possible that you have to look at like a million different conditions to find the most vulnerable set of patients in the database. But that's not really where you want the set of vulnerable patients. You want to be able to figure out if somebody is at high risk very early on. And so it would be nice if we could place the high risk subgroups up at the top. And Corals is not designed to do that. It's just designed to make the model accurate. We also can't use it to make decisions because these are just predictions. There's no costs involved. And it can't produce full binary split decision trees because it's only designed for one-sided decision trees. So I want to mention a few of the projects that we're working on that help with all of these four things. Okay, so probabilistic predictions. This is actually the predecessor to Corals. It's called Scalable Bayesian Rule Lists. And it is a hierarchical Bayesian model that creates rule lists. And there are priors on everything. There are priors on the number of rules in the list and the sizes of those rules. And there's also priors on these probabilities here. And so you can actually run it in a fully Bayesian way if you want to get uncertainty on everything. Or if you want to, you can simply try to get a maximum a posteriori rule list, in which case you'll get probabilities here with uncertainty, with confidence intervals. You'll actually get a full posterior distribution on each of these leaves. Okay, we did a lot of experiments with scalable Bayesian rule lists. Here's a case where we were looking at 1 million observations and 1,000 rules, and it took a little bit longer than CART, but it produced a lot better solution. And also, this is an example where we were using 50,000 observations and 50,000 rules. It took way longer than CART, but again, it produced a better solution. And then if you don't set the regularization parameter high enough, you can end up with kind of rule lists that are way too long. So I wanted to show you that actually can happen. Oh, sorry. Okay, so then, as I mentioned, it would be nice if we could place the high-risk subgroups first. And so we've generalized full scalable Bayesian rule lists and Corals to handle these constraints where the probabilities have to decrease as you go down the list. Okay, so these are called falling rule lists. And if you tried to create a falling rule list in the way that you would create a standard decision tree, then you would have to pick the first rule. You'd have to do it in a greedy way, right? CART is, everything's greedy. You'd have to pick the first rule, and then the second rule, and then the third rule, the fourth rule. And if you made a mistake on the first rule, there's no way to actually change it because these are greedy methods. They don't fully optimize anything. Whereas these two methods, for falling rule lists, they actually fully optimize their objectives. Okay, so for falling rule lists, as I mentioned, the probabilities are constrained to decrease as you go down the list. We've also designed a version of falling rule lists where you can have some slight reversals of these probabilities if it leads to a significant improvement in accuracy. And we made the constraints soft, essentially, so they're called softly falling rule lists. Okay, so for making decisions, we designed a method that includes a lot of different types of costs that you might encounter in the real world and tried to include all of them in the algorithm. Okay, so the algorithm is no longer trying to be more accurate, it's trying to minimize costs instead. Okay, so there's costs for everything. There's costs for gathering information, there's costs for treatment, and there's costs for how effective the treatment is. Okay, so let me give you, I'll tell you what this is by example. This is a treatment, it's called a treatment regime for bail decisions. And the way it was designed was that there were costs that we placed on each of the features. So for instance, these features were given lower costs. And then, so gathering that information is very low cost, whereas these features are much higher cost to get. And then personal recognizance, that is a treatment low cost because it means you just let the person out and assume that they're going to come back for their trial. Whereas release on condition means that you place some conditions on their release, like either you have somebody come and check on them, or you, I don't know, you bail or something like that. Some condition that you place on their release. And this one is much higher cost, but you would want to do it if it would reduce the chance that the person would commit a crime before they came back for their trial. And the probabilities, the effectiveness of the treatment is calculated offline using doubly robust causal inference techniques. Okay, so this particular policy says that for a particular person, we would first check if they were female, if they were on a minor charge, and they had no previous offenses. In that case, the lowest cost option is to release them on personal recognizance. Okay? So then, if the person doesn't fit these three conditions, we have to pay a higher cost to assess the next set of, we have to pay more cost to assess the next set of conditions, which is they have a previous offense in the prior arrest. If that's true, then release them on condition. Okay, and then, so we would pay the cost to release them on condition because it's actually more cost effective to release them on condition because it will lessen their chances of committing a crime, which would be even more costly.
A quick question.
Sure.
How would somebody have a previous offense mean yes?
Sorry,
not
yeah,
have
this
prior?
is it's like a recent arrest.
Oh, recent arrest.
Yeah, sorry about that. Yeah, we should have used better. Okay, and then, okay, so then you pay more for these additional. And then if the person manages to get through here, you've paid all the costs to check all of these things. And then if you still didn't know what to do with the person, you would have to pay a lot more to get more information to figure out which decision to make. Okay, so yeah, so I just wanted to show you that this is kind of how you would turn one of these problems into a policy. There's no sparsity regularization in these models because the costs for calculating all the conditions acts as a sparsity regularization. If you put a huge number of conditions there, you have to pay a huge cost just to get the information, and so you don't want to pay that cost, and that leads to sparsity regularization. Okay, and here's another treatment regime for asthma. So here it says you should give people this very expensive test because the test gives you a lot of information about their treatment. So the first thing you should do is give them this test, check for previous asthma, check for high cough. If so, you give them the more aggressive, more expensive asthma treatment because that's the lowest cost solution, including the probability that they will have a future solution. Okay, and then you would check all these other conditions depending on where they lie. There's a very expensive test in the bottom here. You would only check that for a few people. For the few people who didn't manage to get their decision made by any of the top rules, so they get to this rule, and then it's the expensive test. Okay. So another project that we've been working on is trying to extend the Corals framework to fully grown binary split decision trees. And we've been working on this for the last couple of years. So this is an optimal decision tree for the Broward County data here. And we've been extending it also to real value data, as I mentioned. So this is an optimal decision tree on the iris data set. And this is a very, very sparse decision tree, as you can see, on real value data. So this is an optimal decision tree on iris. And that's ongoing. But this problem is exponentially harder than the problem that Coral solves. Okay. So let me switch over to talking about risk slowing so you can see what we're working on there. Okay, so I want to point out that scoring systems have been used even in criminal justice for the last 100 years, and they're pretty, but this is what was going on in the 1920s. Obviously, they weren't using machine learning to construct their scoring systems, they would construct them by hand, and you would get points for whether you were a ne'er-do-well or a mean citizen or a recent immigrant, something like that. That's pretty bad. But in any case, it worked the same way as the models. You know, you get a certain number of points, and that translates into your risk of violating parole. Okay. So this is a more modern scoring system, which is the Pennsylvania Commission on Sentencing system. And again, you get points, and those points translate into your risk. This is another score. I mean, I could list these things forever. There's whole websites where you go in and you get various scoring systems. This one is for violence appraisal, and this one, the scores translate to low, medium, or high. You get the idea. There's hundreds and hundreds of these things. But there hasn't previously been a method to construct these scoring systems using machine learning. So people would have to construct them by hand. All right, so this is the problem that Recidivism solves, which is minimize the logistic loss to get the risks to be calibrated, the probabilities to be calibrated to the data. And also, this term is a model size term. It's an L0 term, which means try to make the model as small, have as few terms as possible in it. So, smaller number of features. This constraint here, which is that the coefficients have to live in a set L, means that each coefficient is an integer between -10 and 10. All right, so this is a mixed integer nonlinear program. Its feasible set is the integer lattice. It's a very, very hard problem to solve. And if you sent it into Nitro or one of the NLP solvers, you wouldn't solve it. This wouldn't even work for even fairly small data sets. Okay, so we designed our own cutting plane method that combines elements of branch and bound. And in order for me to explain what that method does, I need to give you a short tutorial on standard cutting plane techniques and then show you what we did. Okay, so let's say that we're trying to minimize this objective with cutting plane techniques, standard cutting planes. We would start somewhere, calculate the objective, and then calculate a gradient, like a cutting plane, like this. And then we would try to find the minimum of, well, there's going to be a lot of blue, this is a lower bound. Blue is like a lower bound. So calculate the minimum of the lower bound. Here we know that the function's bounded above 0, so we're going to just use that point for our next iteration. And then just keep repeating it. So calculate the objective and the gradient, our cutting plane. And then again, I have to minimize this here. I'm going to choose that point there. Okay. So now it gets more interesting because now you can see I'm solving a linear program here. I want to minimize the surrogate. And end up right there. And then I calculate the objective and create the cutting plane. Yes. And then, lo and behold, I have figured out that the minimum of the objective is actually on the function itself. And so since the surrogate and the function are equal to each other, I know I found the optimal solution. Now, that's all nice and good. And there's only one problem, which is that it doesn't work for our method, our problem. Okay. So normally you would want to solve this linear program for the standard cutting planes, but for the problem we're working on, which is risk super sparse linear integer models, the solution is supposed to lie on an integer. So the actual minimum of this objective that we want might actually be over here because we're only working on the integer lattice. The solutions all have to be integers. So in order to get to this point, you would have had to solve a mixed integer program at every iteration to find the smallest of these points. Now, solving mixed integer programs gets expensive. It's not as bad as solving the min-LP directly, but solving the mixed integer programs, the more cutting planes you put in there, the larger and larger the mixed integer programs become, and they become more and more infeasible by the minute. And at some point, the solver just chokes, and you just can't solve it. And you have to solve these MIPS to optimality, because if you don't solve them to optimality, then you never know when you have the optimal solution to the actual problem you're working on. So essentially, you're forced to solve bigger and bigger mixed integer programs and you're forced them to solve them to optimality. So it's just a bad overall situation, and you end up with the solver just, as I mentioned, just completely stopping and saying, no, sorry, can't. So this is after 70 cutting planes have been added. This is the time it takes for the solver to solve that MIP. And it just, at some point, it just says, nope, I'm not doing it. I'm going to take over 10,000 seconds, and then we just turn it off. And then the optimality gap, which is supposed to go down to 0, it stays at 100%, and it never drops down to 0 at all. So you're just totally stuck. So cutting planes standard cutting planes don't really work for this problem. So we came up with a solution where we would actually solve the LP, not the MIP, right? Solving linear programs is much easier than solving mixed integer programs. So we solved a linear program, and then if the solution of the linear program happened to lie on an integer point, then we can add a cutting plane. And if it doesn't, then we know that there's no solution in here, because there's no integers in here. So we can actually handle each of these parts separately, the same way you would do in a branch and bound problem. So we block off this whole part of the space and handle this separately from this. And then when we minimize, for instance, with an LP, we might end up right here the next time, in which case we can create a cut. And so this method where we solve the LP, either create a cutting plane or subdivide the space, this actually seems to solve the problem. And where before the solver was choking at 70 iterations, here we can run it for over 10,000 iterations, and it still doesn't take more than 100 seconds per iteration. And the solver, the optimality gap, which is, as I mentioned, supposed to go down to 0, sort of nicely falls down and goes towards 0. Okay, and one very nice thing about cutting planes is that because the solver never actually sees the data. Right? The solver only sees the cuts. And so you can run this thing with huge amounts of data, and the solver never has to deal with that. So even if you scale it up to 10 million iterations, the time spent on the solver remains relatively constant. 10 million points, 10 million observations. So even if you scale the problem to these huge data set sizes, the time on the solver stays about constant, whereas the total time increases linearly with the amount of data and not exponentially, because you're using the data to evaluate the function, create the cutting planes. But that stuff is all done under your control, and it's all linear. The solver just looks at the cuts. Okay, so we've been applying this to a lot of different problems, working mostly in conjunction with doctors. And I'm just going to show you the scoring system that Burke created with our collaborators. Ron Kessler was our main medical collaborator at MGH. And Ron had been struggling with creating a scoring system for adult ADHD screening and diagnosis, because he was fiddling with trying to reduce the number of features, like sparsity, and trying to assign points. And the reason he was struggling with this is because they recently changed the criteria for what constitutes ADHD to make it less stringent, so that he had to actually change the whole scoring system to agree with the new definition of ADHD. So this is the scoring system that Earth produced. So I'll sit that on the slide for a few minutes while I talk, and you can figure out whether you're likely to have ADHD. The nice thing about this model, according to our collaborators, is that there are some conditions in here that get at how much people need to depend on other people, how much you need to depend on other people, like how often do you depend on others to keep your life in order, and also things like procrastination, how often do you put things off until the last minute. And so it doesn't just repeat the definition of ADHD, it actually gets into sort of other interesting things that are important. Okay, this is a project we've been working on with Aaron Struck and Brandon Westover, who they both lead critical care units in hospitals. Brandon Westover leads the critical care unit in the Massachusetts General Hospital, and Aaron is at the University of Wisconsin. And our goal was to take these patients who have just had a stroke and they're in the ICU and try to predict whether they're going to have a seizure. So if you have an aneurysm that bursts, you have a hemorrhage, subarachnoid hemorrhage over here, you can see it. So the patient then gets surgery done on them, and then they end up in the ICU. If they have seizures while they're recovering, those seizures cause brain damage, and they're very, very bad for you. It can cause a lot of problems. And so we want to predict these seizures before they happen so that the doctors can give the proper medication. And you wouldn't just give people medication because the medication is also dangerous. So we have to predict fairly accurately when the patients are at risk for seizure. And also we need to know when the patients are not at risk for seizure, because these monitors, these EEG monitors, are really expensive. And we want to take people off the monitors who are not at risk and give them to people who need them. Okay, so yeah, seizures are common. 20% of people have them. They cause brain damage. You need EEG to detect them, and it's expensive and not well utilized because there's no mechanism for prediction of illness. Okay, so we want to predict seizures to determine who needs the monitoring. And this is the model that we came up with. It's called the 2 helps 2B score. 2 helps 2B is 2H, E, L, P, S, and 2 points for the B. So the doctor can just memorize the name of the model and they know the whole model. Okay, and these models were chosen from over 70 variables, and the data set we used was from the EEG, Critical Care EEG Monitoring Research Consortium, which Brandon Westover leads. Okay, so the 2 helps 2B score is currently used in 5 different hospitals, and 5 or 6 different hospitals. And in Massachusetts General Hospital and Wisconsin, they actually did a lot of work to try to estimate the savings from the use of this model last year. So this model is just as accurate as black box models we compared with. Doctors are not forced to trust it. They can decide themselves whether they want to trust it. It led to a 63 somewhat percent reduction in the duration of EEG monitoring per patient in 2018 at these 2 hospitals. It led to, this one is apparently the big deal, that it's led to 2.82 times more patients being monitored. This is the one that the doctors are really interested in. And it's led to over a $6 million savings for monitoring in these 2 hospitals last year. Okay, and I should mention that the code for these methods everything is publicly available. Corals has its own webpage, and you can download Python, the R interface, and it's the code is actually in C, but it has these interfaces. Okay, so the takeaway is that these are hard problems, but we can solve them in many real cases, and they lead to practical solutions that we can actually consider the possibility of using. Now, our former undergrad did a calculation for corals that I really like. So take the ProPublica data set, which had 155 rules that were mined. If you did a brute force calculation of all rules up to length 10, that's 6 times 10 to the 21 different rule lists. And if it takes 2 microseconds to evaluate a prefix on a MacBook Air, that's going to take 30 million years. So to calculate the optimal rule list by brute force could take you 300 million years. Okay, luckily Corals is 33 trillion times faster, and it only evaluates 180 million different prefixes and finds the solution in under 10 seconds. And it takes 2 to 8 minutes to certify optimality. Now, Ryman, when he invented the CART algorithm, he couldn't have implemented Corals, even if he had thought of it, because that 2 microseconds would have taken him something like, much longer, and the 2 minutes it takes us to certify optimality, it would have taken him 4 years, because computers are about 1 million times faster than they were. Okay, so let me just briefly tell you about one little bit of ongoing work that my lab is doing, which are we're working on interpretability for computer vision problems. And in computer vision problems, the only techniques right now that seem to be really working for image recognition are deep neural networks. And the form of interpretability is completely different, right? You can't do decision trees on pixels. It just doesn't make any sense. The sparsity makes no sense here. So we've been designing algorithms that use case-based reasoning to try to do classification for computer vision problems. And we still haven't noticed that there's a huge decrease in accuracy when you create a neural network that's interpretable. So this is an example of our neural network classifying a clay-colored sparrow. And what it does is it takes the image and it looks at specific parts of the image that help it to identify what kind of bird it is. So for this image, it would say that part of the image looks like that thing, that part of this image, and this is a prototypical clay-colored sparrow. And when I say this part, what I actually mean is this part of the image. Okay, and then it would say, okay, also, I think this part of the image looks like that part of a prototypical clay-colored sparrow, which is over here. And so here it's looking at the feather patterns and the feet. It's essentially looking at the most important parts of the image and comparing it to nearest parts of prototypical cases. So it's not k nearest neighbor, it's sort of k nearest parts of prototypical cases. Okay, that's it.
We're a little over time, but we can take a couple of questions. Please.
In the course algorithm, you're just working with binary covariates, right?
Yeah.
If you want to extend it to categorical with many classes, you can just binarize again.
You could do that.
But then, if you have a categorical variable with 5 categories, and you take the one that is appearing in the decision rule, then how do you avoid that the others are going to be exceeded?
Well, I mean, first of all, the objective function that I created is only for binary classification, so we need to change the objective function. We're actually working on that right now for the optimal decision trees.
Okay.
So you actually have to change the objective function and rederive all of the bounds in light of the new objective. And so, yeah, that's something we haven't done and we're working on. We're also working on things like how to handle imbalance in data, where you want to weight one class over the other class, or trying to optimize things like area under the RC curve and other objectives. Yeah.
For the mixed integer programming problem that you were addressing, you were working on a lattice between -10 and +10. I would have thought that we might treat it as a continuous random variable, find the solution in the continuous version, and then look for nearby integer solutions that are about as good. Is that?
Yeah, you could do rounding. The problem with rounding is that when you round, you might actually be moving against the performance gradient. And so that's the whole reason that the field of mixed integer programming was sort of invented, was because rounding doesn't usually achieve the optimal solutions. It's not that easy for me to explain exactly why that's true, but you can think about very long, elongated, like think about ellipsoids that are very elongated, and the solution is at the minimum in the center of the ellipsoid, something like that. And let's say you're sort of on the edge of the ellipsoid and you round, then you actually go just against the performance gradient.
Right.
And the norm. So for the scoring systems, what might happen if you try to round an L1 solution is you might send pretty much everything, all the coefficients to 0. Because L1 solutions have lots of very, very tiny coefficients. You round them all, they all go to 0. And you just end up with like 3 coefficients that are non-zero, and they're not very small, big, and those coefficients don't work very well. Yeah, so. In the Recidivism paper, there's a whole lot of experiments where we've tried different interesting rounding techniques. We invented our own rounding techniques, and they just don't work as well.
Anything else? Well, please.
In your experience with some of these projects, for the scoring where you give a risk, I saw that there was an example of the categorical output versus the percentages, and I understand that you don't want to really classify anything, but you want to give an idea of like the risk. What has worked there for like people that are using these scoring systems like that?
Sorry, I don't understand.
So the percentage risk versus the categorical kind of risk. What has been your experience and what has
Oh, I think it just depends on the problem, which one you want. Yeah, I don't think there's a right answer whether you want a probability or you want a yes or no prediction. It just depends on what you're doing. You know, because it could be that you just have to make a decision and the probability is not useful. Like, am I going to send this advertisement to you or not? Like, I don't really care about the probability. I just want you to click on that advertisement. So should I send it to you or not? Or is this a cat or is it not a cat? I don't need to know the probability that it's a cat. I'm just going to classify it as a cat and then act accordingly, something like that. I don't know. It just, like in Facebook, I just have to label it as a cat.
Yeah.
So I think it just depends on the problem that you're working on, whether you want the probabilities or if you want the actual predictions.
But the interpretation of those probabilities for the people is important too, right? So the way you can translate this into even a probability might be, it might be something for you, but not exactly the same for the person who's using the scoring system. So,
Well, it's all calibrated to data. So you could always recalibrate it if you had a different data set. Then want to rebuild them all, probably.
We're going to have to end now, but thank you so much, Cynthia.